This is Unit 5, Lesson 2, wherein we move from the radian measure as a concept to starting to use it as a tool. I think this is an important lesson. In a lot of ways, it should be something you know already from grade 11, but my experience is that this is a very big idea, and it's also a fairly complicated idea, and I don't find too many grade 11 students necessarily absorb it fully. So I'm going to sort of try to teach it, as though you may have seen it before, but may not know. I'll try not to count on too much, I guess is what I'm trying to say. I'll try to be as first principles as possible. We're going to start with something called the special triangles, which you can see there are two triangles whose trig relationships are fairly easy to know because the numbers on either side are not super complicated. So in the first triangle, which is the one over here, we have two sides which are the same, right? So we have that side and that side, and then we have a third side. Sorry, I'm going to be very poor at drawing these things with my tablet. It's just not something I'm very good at. This is a 1, this is a 1. Sorry. This is a 1, this is a 1. Now, if you think to yourself and think of a right triangle, right? You know that in a right triangle, we know that a squared plus b squared equals c squared in terms of finding the hypotenuse. So, of course, here 1 squared plus 1 squared is equal to root 2 squared, right? 1 plus 1 is 2, and then you have to square root it, so you get root 2 on this side. So if you square both sides, you get 1 plus 1 equals 2, right? Which is of course, where that's coming from. Now, the other thing about this triangle is that as we're used to thinking about it, the two angles on it are the same, and they are both 45-degree angles. Now remember, a 45-degree angle is a 180-degree angle. If 180 is pi, sorry, I really wish I knew why my tablet would stop working when it goes to the side. I'll hopefully get this fixed if this goes on much longer. Sorry. If 180 is the same thing as pi, right? So remember, an entire circle, or semicircle, is an angle of pi. Then you think about a 45-degree angle, right? Is that same 180, but split into 4 equal parts, right? Each part would be each part would be 45, so that the whole thing makes 180. So in the same way, if you split pi into 4 parts, now again, here's where we go back to the idea, I don't want to know what pi divided by 4 is as a number, but I can write pi over 4 as a symbol and just represent a quarter of a semicircle, right? And that's kind of the idea here. This is a pi over 4. This is a pi over 4. In the same vein, what used to be 90 is now a pi over 2. And of course, they'll just write it just to complete it. A 45 is a pi over 4, right? Because of course, 2 45s, so this one plus this one makes 90, right? And so that's the idea. So instead of thinking about this triangle as pi over 4, 45, 45, 90, we can think of it as pi over 4, and pi over 2. Now the same thing can be used over here, right, with this triangle, where we've got, sorry, that's greatly exaggerated how long it should be, but you get the idea. 1 to root 3 to 2. And once again, it's just a Pythagorean theorem thing, right? 1 squared plus root 3 squared equals 2 squared, because 1 plus 3 equals 4, right? Is once you do the squaring. Now, once again, it has a 90, and we know that the 90 is pi over 2. Now, a 60, right? How should we think about a 60-degree angle? Well, a 60-degree angle goes into 180 3 times, right? 60, 120, 180. So of course, when we think about it now, really a better way to think about it is just a third of a semicircle. So pi over 3. 30 is something that goes into 180 6 times, so we will think of it as pi over 6. Once again, if you draw pi over 6, you're just drawing 6 equal 1, 2, 3, 4, 5, 6 parts. If each one is 30, it's 30, 60, 90, 120, 150, 180, and you still get, 6 pieces is equal to 180. Therefore, we're talking about pi over 6, because remember, 180 is pi. So this is the idea with the two special triangles, and what we're going to do now is calculate their trig ratios. So let's just remember how to do that here. Okay, so to calculate a trig ratio, what you're going to do is, use SOHCAHTOA, right? So you're looking at the 90-degree triangle, and you are doing either the opposite. You're looking at picking an angle to look from. So let's say we're looking from this pi over 4 angle right here, okay? And then what you're doing, if we're looking from that angle, this would be the opposite. This would be the adjacent, the side that's beside it, and this would be the hypotenuse. Now, the hypotenuse, remember, is always across from the right angle. Now, what I just did depends on, right? It depends on what angle you're looking from. For example, if I'm looking from this angle, then the opposite is the side over here, right? If I'm looking from this angle, wow, that is magical. The opposite is over here, okay? Just make it something more. Yeah. Okay. All right. So it depends which one you're looking from, of course, right? Let's start with the pi over 4 because that one's kind of the most straightforward. If you're looking for pi over 4, right? So this is pi over 4. Its sine is 1 over root 2. Its cos is also 1 over root 2, since whether you're looking for the opposite or the adjacent, both values are 1. Since the opposite and the adjacent are both 1, the tangent is 1, because the tangent is, of course, 1, the opposite divided by the adjacent. Okay, now let's look from the perspective of 30 degrees. 30 degrees is, and I'm going to use my green here, just okay, this is the 30-degree angle. This is a pi over 6, right? So pi over 6, as opposed to this one, which is a pi over 3. And the sine, okay, well, what would the sine be? 1 divided by 2. 1/2. The cos of pi over 6 would be root 3, which is the adjacent side, divided by 2, which is the hypotenuse. The tangent would be the opposite, which is a 1, divided by the adjacent, which is a root 3. Okay? Now to finish this off, we'll look from the 60-degree angle, which we can now describe as pi over 3, or 1/3 of a semicircle. The sine of such an angle would be root 3 over 2. Root 3 over 2. The cos of the angle would be the adjacent divided by the hypotenuse, which would be 1/2. And the tangent would be the opposite, root 3, divided by the adjacent of 1, which is root 3 as the tangent. Okay? And those angles are really important. Okay? Special triangles can be used to determine trigonometric ratios and their reciprocals on the coordinate plane. Now this is the big idea we're moving towards today. Okay, so page 2 is here. To wrap this up, all of these ratios are ones you should be able to verify by yourself. You should be able to create these triangles, right, and then get their ratios. Now, you may eventually memorize these because we use them a fair bit, which is good. But I don't think you necessarily should think of them as the memorizing in the memorizing way. I would just know how to draw the triangles and quickly recreate them, right? Sort of like as we did here. We just recreated the two triangles, labeled their sides, and then if I needed the sine, the cos, or the tan, I just use my knowledge to generate them, right? I think you're probably better off approaching it that way. Now, this brings us to one of the primary, I guess, ideas of this unit, which is how do we deal with angles as they get outside of a triangle. So like within a triangle, of course, the sine, the cos, and the tan are all values that, you know, we understand. It's a right triangle, the hypotenuse is one side, the adjacent's one side, the opposite's one side, and we know that trig is essentially a study of those ratios. But we also know that trig can go beyond the first quadrant and therefore go beyond 90-degree angles, and of course therefore go beyond right triangles. It can be used in bigger triangles, and it can even be used in values that don't even make a triangle, right? Like for example a 200-degree angle that's bigger than any triangle could be. So that we know what we're talking about, we choose a specific way to represent angles. We start angles always at the positive x-axis. This is called the initial arm. Okay, this is the initial arm here. It's where you're going to begin measuring any angle that's in so-called standard position. Okay, standard position, really important idea. To measure your angle, what you're going to do is you're going to start to turn counterclockwise as far as you need to go to draw the subsequent terminal arm. Terminal just means end, right? So the beginning arm is always the positive x-axis. The terminal arm is always rotated in a counterclockwise direction from the x-axis. Okay, that is what we mean when we say something is in standard form. And as you can see, like our typical Cartesian plane over here, there would be ultimately four quadrants that our angle could rotate through before our angle did a complete rotation and just started over again, right? And this is one of the things to understand about angles as opposed to regular numbers, is that every 360 degrees, or every 2 pi rad, angles simply repeat themselves, right? Whereas regular numbers, right, if you count to 10, and then you count another 10, and then you count another 10, and another 10, you never go back to the number you started at, right? 20 is bigger than 10, 30 is bigger than 20, 40 is bigger, 50 is bigger, and you just keep counting and they just keep going. That's why in the course up until now, when we were talking about numbers, we were talking about a number line, right? You could go all the way from negative infinity to infinity, and you never repeated a number ever. Now angles are not like that, right? Because angles, you go through your pi radians and then you just repeat them, right? So 2 pi radians, for example, is the exact same as 4 pi radians, because once you've gone through 2 pi and done a rotation, you know, and then you go through a second rotation, you still just ended up at the same place. And for that matter, 2 pi is the same angle as 0, right? 0 is the same angle, 2 pi is the same angle, 4 pi is the same angle. Because imagine you're facing your computer right now, or you're facing forward, and then you turn 360 degrees. You haven't actually changed the way you're facing, right? You're at the same angle you were when you started. And this is just something important to consider. So like when we, for example, say 45 degrees is the same thing as 405 degrees, the idea is that 405 degrees is a full rotation after 45. The same way we could say pi over 4 is the same thing as 9 pi over 4, right? Because 9 pi over 4 is 2 pi bigger than pi over 4, and hence the same number. Now, we don't always have to rotate in a counterclockwise way. We do that when the angle is positive. We rotate in a negative way when we're rotating clockwise. Okay, so if you have to draw a negative angle, one of the things what you can do is you can draw your angle going this way, and that would be a negative angle. Now, of course, no one ever has to work with a negative angle, because if I tell you to draw negative 120, right, someone might say, well, sure, sir, I could draw negative 120, but why don't I just draw positive 90, 180? Now, I know if I went all the way down here, I'd get to 270, but I don't want to go all the way down here, so I'll get 240. Now, of course, 240 and 120 make 360, so I know it's a full rotation, so 240 is equal to negative 120. And I never actually have to draw a negative angle. I could always just draw the positive angle that goes the other way to get me to the same place. And by the way, in the same way as the argument I just made, you'll notice that these two numbers are separated, right? 240 take away negative 120 is 360. They are separated by 360. Negative 120 plus 360 equals 240. This means if I give you a negative angle, like negative pi over 6, one thing you can do is you can take negative pi over 6 and add 2 pi to it, and therefore generate yourself a positive angle, if negative angles are not your thing, or if you find them hard to work with. 11 pi over 6 as a positive angle is the same thing, and let's just show that quickly here with an example. So let's create it. Let's create a terminal arm and an initial arm, right? And you can do this too if you want. So we're going to type O, and basically what that does is just make a point at the origin. We're then going to type 1, 0. Okay, and 1, 0 makes a point over here at 1, 0. We'll draw a segment that connects O to A. Okay, now this thing that I just drew is my initial arm, right? So we could rename it. Just call it initial arm. Okay, and that initial arm goes from O to A, and okay, so be it. Now we're going to draw. We'll create a slider, and we'll say I want it to be an angle. Now by default, it'll start with 0 rad. It'll go up to 6.28 rad, which you know is full rotation, and the increment is, you know, whatever. Now what we're going to do here is we're going to say rotate, and look at what it asks for. It says what object do you want to rotate and what angle. So let's rotate initial arm, and let's rotate it alpha radians. Now to make alpha, I typed Shift A. Okay, sorry, excuse me, Alt A, not Shift A. Now you can do that, or in the bottom corner here where you have this, this is all your like symbols. So alpha is right here, right? So you could just put alpha there. So we're going to rotate our initial arm alpha rad. And then what we're going to do is we're going to say, let's measure the angle from A to O to A prime. And of course, the angle will measure at what we said, right? Which is 0.7854 rad for our purposes here. Now we can move this, right? And do so. And then yeah, okay, so let's imagine, right? Let's imagine we had to draw what I just said. So alpha equals negative pi over 6. Now what does GeoGebra measure here? You notice it does not measure a negative angle. It just gives you a positive angle. And because, you know, one way of getting from A to A prime is to rotate pi over 6 in a negative direction. Another way to do it would be to go 11 pi over 6 in a positive direction. And just to prove that to you for a sec, 11 pi over 6, if I type that in, I get 5.75959, the same way that GeoGebra measured it here. Okay, so when you see a negative angle, it's up to you. I mean, there's no harm in just treating a negative angle, and drawing it. But for some things that we do, you might find it easier to just switch it to a positive angle. That's one of the advantages that we can do in angles that we could not do with regular numbers, right? You can't just change a regular number into a negative or into a positive unless you're prepared to factor something or move something to the other side or whatever. But you can't just say 6 is the same thing as -6, right? You can do that with angles. So you're always free to describe an angle as a positive number or as a negative number, because they both get you to the same place. Now, so the idea behind standard form is that we can all agree, when I say, for example, draw an angle that's pi over 3, we will all draw the same thing, right? We'll all draw something starting at 1, 0, coming into the origin, then going up and to the right with an angle here of pi over 3. Okay, and that's what standard position is all about. Now, the second thing that standard position is good for, or rather is used for, is we can say that a point has an angle. Okay, a point has an angle. So for instance, if we go back here and we just draw a random point, right? Let's all draw, -3, -2, right? So we've got a point over here. Now, how could I say that point has an angle, right? What I can do there is I could say, well, if all of us start at the positive x-axis and all of us rotate this way, right, then technically all of us would draw the same thing to get to B, and all of us would agree that that B represents an angle in standard form. Let's show how this might work. Okay, so I'm going to draw my initial arm again. I'm going to rotate it around and point it towards B, and then I'm going to how do you do this again? Dilate. Let's make another. So just make a random number here. And then what we're going to do is we're going to dilate the initial arm, by a factor of b. Okay, so we're going to dilate it, which basically just means make it bigger, and we'll make it bigger. And you can see my angle's a little bit off here, so let's sort of rewind it a tiny bit, and now you can see that point B has an angle in standard form. It has an angle of 3.728, whatever, right? And it's important to realize that point B was just a number I just picked out of thin air, right? I could pick any number on the Cartesian plane at all, any number, and find that it has an angle that's connected to it, because I could always start from a positive x-axis, and I could always rotate around until I found the point I was looking for, and then I would create an angle that connects, right? And that's what this diagram is meant to show. P is a point with x and y coordinates, and x, y coordinates connect to an angle, and that's the big thing to take away from this. Any point on the plane has an angle in standard position. Okay. Now, this leads us to what does it mean, okay, to take a trig ratio outside of the first quadrant. And to do this, what I think we should do is let's go back, let's delete some of the things we were making here because we don't need them anymore. And we're just I'm gonna try and create a demonstration here that's hopefully gonna show something useful. Now, this point here, A, okay, there is something special about the point that the angle represents. So you can see that, like, depending on how I rotate this thing, A prime moves in different places, and of course if we follow what A prime does, we know it's making a circle, right? It like creates a circle as you rotate all the way around, right? But there's something else that A prime is doing which you might not notice right off the bat. So what I'm going to do is I'm going to draw a new point with the same x value as A prime. I do that by saying x bracket A prime and then 0. And I'm going to draw myself a triangle okay, a segment that connects B to A prime. Okay, now what I'm doing here is I'm drawing myself a triangle. Okay, so let's say polygon. Just so polygon from O to B to A prime. Okay, so we've got a little triangle here. Now, here's the thing about the triangle. The angle in standard position that we are drawing, okay, the angle from A to O to A prime, is an angle inside a right triangle. Therefore, it has trig ratios. Now, even if I move this to a different part of the circle, I can still draw a right triangle. I know the angle is out here, right? The angle's not in my triangle anymore, but I can still draw a triangle, and that triangle still has trig ratios. In fact, we could even draw it down here, right, in quadrant 3, and you can still draw a right triangle, even though you're in quadrant 3 and your angle here is way too big to fit a triangle. Finally, of course, in quadrant 4, we can do the same thing. So we can draw, okay, a right triangle in all 4 quadrants, and in each one we can sort of still be connected to the original angle that we were supposed to draw. Now, the last thing I want to say about this is let's focus our attention on the actual coordinates of A prime. Okay, now of course when you see the coordinates, you know, they don't look like anything. I mean, they just look like, you know, numbers over here. But here's the point I want to make. Let's type the sine of alpha over here, okay, and then we're going to actually calculate it over here. Okay, so we'll type sine. Now, something is interesting here about the coordinate of A prime and the sine of this angle. Watch as I move the angle. Let's make the angle a little smaller. Now, if I measure the sine, okay, which is the opposite side over here divided by the hypotenuse, I calculate that the sine is 0.46067. But look carefully at my circle. My circle, the value on my circle, the point, the coordinate, has a y value of 0.40674. As I change this value, the sine of the value and the y coordinate are the same. And we can extend this a little further, right, to check the cos, for example. And the cos of the coordinate, of the angle, excuse me, is equal to its x coordinate. So notice that all these values in quadrant 1, my cos is equal to my x coordinate. My sine is equal to my y coordinate, right? So here, for example, this is the one where we did pi over 6, right? Pi over 6 is the number I'm looking at now. It's 0.5236. It has a sine of 0.5, like we calculated on the first page, and it has a cos of 0.86603. That number is root 3 over 2, right? The one we found on the first page. Now, when you do the same thing, okay, and you notice that as I go through this, the sine and the cos track the point perfectly. Okay, the sine and the cos are the same as the point everywhere I look, even at a 90-degree angle. The cos is 0 and the sine is 1. Even at a 0-degree angle, the cos is 1, the sine is 0. What happens when I bring this into a quadrant that is too big to draw a right triangle? Well, what happens is the coordinates still tell me the answer. Okay, this is a big idea. My x coordinate has become negative. It is negative 0.66913, which is the cos of my angle. even though my angle is too big to be in a right triangle, my angle is related to a right triangle in the second quadrant. This triangle on the left has a cos of 0.66913 and a sine of 0.74315. But my number, which is bigger than quadrant 1, has a negative cos and a positive sine, because in this quadrant x is negative but y is still positive, right? Y is the sine and y is still positive. When we move into the third quadrant, since x is negative and y is negative at the same time, I'm expecting both sine and cos to be negative in that region, right? So look, cos is negative, sine is positive. Then we go into quadrant 3, and now both of them are negative. Both x and y are negative in quadrant 3, and quadrant 3 is values that are bigger than pi but smaller than 3 pi over 2, or maybe more you're used to, they're bigger than 180, they're smaller than 270. When we bring the circle into the final quadrant, we see that cos is positive because, of course, we're back on the positive right side of the graph, but we're still on the bottom half of the graph, so sine is negative. Now this gives rise to something called the cast rule, which is right here. If you think about x and y, okay, so think about an xy coordinate, xy, okay? The first coordinate is positive, positive, because that's the quadrant that you're in. The second coordinate is negative, positive, because cos is negative, like the x numbers are negative, but the sine is positive. Now remember, the tan is equal to the y value over the x value, right? Because the tan is equal to the sine over the cos. So let's just quickly do a sine, cos, and tan in each one of these things. Okay, so here's what we're going to do. So once again, imagine we have an x and a y. In the first one, we have positive, positive, and our tan is going to be positive because it's going to be, y over x equals positive. Let's write it like that. I guess it'll be more useful. Okay, second quadrant. Cos is negative, sine is positive, y over x is negative, clearly, right? Because one's negative, one's positive. Now, why do we call this quadrant S? Is because only sine is positive in this quadrant. Cos is negative, tan is negative, sine is positive. So you see, we call this quadrant S. In this quadrant, cos is negative, sine is negative, but y over x is positive. Right? I'm sorry, this is... I eventually will get better at using this thing, but y over x is negative over negative. Y over x is a positive in this quadrant. So cos is negative, sine is negative, but tan is positive. Hence, we call this the T quadrant for tan, for cast rule. Lastly, we have positive dash negative, and of course y over x would be negative. So once again, tan's negative, sine's negative, cos is positive, so we call that quadrant C. C is positive, all are positive, sine is positive, tan is positive. Okay, that's the cast rule and where it comes from. Okay, it comes from the idea that the x coordinate is cos, the y coordinate is sine. All right. Now, let me do one last demonstration with this. Okay, which is I'm going to create a graph. Okay, and what it's going I'm going to create a new point, and let's stop tracing this because I think we're going to be tracing a little too much stuff. Let's just draw ourselves the circle O with radius 1. Okay, and then I want to get rid of the okay, so we're going to draw a circle. All right, so there's a circle. Now, I want to create a new point. Okay, I'm going to call it P, and I'm going to let P, for its x value, I'm going to let it have alpha. For its y value, I'm going to collect the y value of A prime. Okay, and remember, the y value of A prime is the sine of the angle I'm looking at. So right now, right, where is my point right now? Well, alpha is 0. Okay, so my point has a value of 0 for x, and the sine of alpha is 0, which means my point has a value of 0 in the y. Let's make the angle a little bit bigger. So let's say right here, for example. Okay, now what's happening right now? My angle is 0.5236 rad, so my x-coordinate is 0.5236, and the sine of my angle is 0.5. That is the y value. Okay, now I'm going to trace this, and I want you to watch the pattern that it creates. Okay, so what am I drawing? I'm drawing the angle and the y coordinate of my circle. Now you can see the y coordinate right now is going up, 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 up. The y coordinate is rising, 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 rising. And then the y coordinate reaches a peak. Now keep your eye on the y coordinate. Oh, sorry, it's going to be a bit off the page here. Oh, lovely. Let's try that again. Okay, so there it goes. Now watch the y coordinate. It drops, 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 drops back to 0. Then it falls all the way down to -1, and then it comes back to 0. Notice, now look at my graph. My graph took exactly pi. Let's draw x equals pi. My graph took exactly pi to come all the way up and all the way down, and then go all the way down and come all the way back by 2 pi. And again, I know it's annoying to see. It's hard to get all this on the screen at once. Okay, so let's just go through it one more time. Okay, so as my y coordinate goes up, down, negative, and back up, it creates the graph of sine x, right? This is the graph of sine x. Okay, and this verifies the idea that the y coordinate of the graph is the sine of the angle. The x coordinate of the graph is the cos of the angle. Okay. Now, the circle I made, okay, was a special circle. It's called the unit circle because it has a radius of 1. And that's important because in every calculation that I just did, remember, sine and cos is a question of opposite over hypotenuse, right? Or for cos, or excuse me, for sine, or adjacent over hypotenuse. But in my circle, the hypotenuse is the radius of the circle, and my radius was always 1, which meant that when I found the coordinate, I just had to divide it by 1 in order to get the sine, or in order to get the cos. When you do this, sometimes you'll be working with a circle with radius 1. Sometimes you'll be working with a circle with a bigger radius. If it has a bigger radius than 1, we'll have to take that into account when we're trying to find the sine and the cos, which is what we're going to do right now. Now I want to just look, yeah, okay. Alright, so let's try an example like this, okay? So I know heavy on the concepts, right? It might be important to go over some of the stuff we just talked about at a future date, right? Or rewind it and have another look at it. Let's try an example. This one says the point -3, -6 lies on the terminal arm of an angle in standard position. Okay, you know what? Let's take advantage of the tech here. Actually, sorry, let's keep that up instead in case we need it. But sorry, they said -3, -6, right? I'm just going to use the. Let's use a proper surface to draw on rather than my terrible estimates. Okay, so this is what they want us to look at: -3, -6. So there's the point P. Okay. The question is, what is the angle in standard position? Okay, determine the exact values of sine, cos, and tan. Then find the radian value of the angle to the nearest hundredth. Okay, this is a big question, and this is a guaranteed test/quiz question. Okay, this is the main skill of the unit. So let's review how do you do this. So the first thing I'm going to do is I'm going to connect this. This is so hopeless. Try this again. Okay, sorry. Change to my pen. Sorry. Not sure what's going on here. Okay. First thing I'm going to do is I'm going to connect this thing to the origin. Okay. So let's do that. So we're going to draw. Okay, not too bad. Better than I expected. All right. The angle is here. Now, as you're getting used to this, I would suggest we just get in the habit of saying that's pi over 2, that's pi, that's 3 pi over 2, and this is 0 or 2 pi. Okay, so just to try to get the hang of like where things are basically. You can tell our point is in quadrant 3. Our angle is sorry, let's write this out properly. Our angle is somewhere. I'm just gonna make the eraser a bit bigger while I. No, I'm not. Okay. Our angle is somewhere between pi and 3 pi over 2. Now, roughly speaking, pi is 3.14. And 3 pi over 2 is like 4.8. Let me get the exact number. I might as well get it. Let's just do 3 pi over 2. Excuse me, 4.71. Okay, so I just think it's useful to try to get these values, you know, these rough values in your mind, right? So let's just write this out. I'm going to zoom this in a bit because I'm having a bit of trouble drawing it from this range. Okay. So our answer, we're expecting an answer somewhere between 3.14 and 4.71, right? Somewhere in between pi and 3 pi over 2. Now we also know that in this quadrant, CAST, we are expecting the cos of our thing to be negative, the sine of our angle to be negative, but the tan of our angle should be positive. Okay, and that's what we're going to just find right now. So how do you do this? Remember, all of this relies on drawing a triangle. Okay, drawing a triangle that is a right triangle that has these relationships. So once again, okay, this is my. So I'm going to call this little angle in here beta. Okay, beta is the angle that's inside my triangle, okay, from here to here. Now, if this is true, okay, -3 is my adjacent, -6 is my opposite, and my hypotenuse, I'm actually not sure what my hypotenuse is, right? We should figure that out. Let's create a relationship here between the sides of the triangle. X squared plus y squared equals r squared. R is the radius of the circle, and r is the hypotenuse. Okay, hypotenuse equals r. So sine would be y over r. Cos would be x over r. Tan would be y over x. Okay? This is really important. How do angles and points connect to each other? Is everything you need to know is in this little green block. X is a coordinate, y is a coordinate. R is a radius that connects from the origin directly to the point. Okay, so directly across like that is the radius. Okay, x squared plus y squared equals r squared because of the Pythagorean theorem. And r, of course, will always be a positive number because even if I have negative adjacent and negative opposite, I still have a positive hypotenuse because the hypotenuse is the result of the Pythagorean theorem. When the numbers get squared, they become positive. Let's see if we can calculate this now. The sine of the angle, okay, well let's find the radius first, okay? So that's of course the first thing we're going to do. So the radius, okay, so we're going to say negative 3 squared plus negative 6 squared equals r squared. So this is 9, this is 36, this is r squared. 45 equals r squared, r equals root 45, okay? So what we just discovered is that the values that we're looking at, okay, the value that we're looking at for our particular question, the sine, the cos, and the tan, we don't have to calculate anything for those things. We just have to know the relationship. So for our question, the sine of our angle is the y-coordinate, which was a negative 6, and the radius, which is a root 45. The cos of our coordinate is negative 3 over root 45. The tan of our coordinate, which is y over x, is negative 6 over negative 3. The tan of our coordinate is therefore 2. Okay? The tan of our coordinate is therefore 2. So now the question is, what angle? Okay, so this is the answer to the first part of the question, okay? So they said the point negative 3, negative 6 lies on the terminal arm of an angle in standard position. Determine the exact values of sine, cos, and tan. Okay, well we did that, right? Sine, cos, and tan, we found them. Negative 6 over root 45, negative 3 over root 45, and 2. Let's prove it. So here I'm going to draw a point at 1, 0. Okay, so here's a point at 1, 0. I'm going to draw a point at 0, 0. And then I'm going to say, what's the angle that connects B to C to A? Okay, and you can see the angle is 4.24874 rad. Now, of course, how do we get that is our next challenge, and we'll deal with that in a second. But let's measure the sine, cos, and the tan. Sine of alpha, cos of alpha, tan of alpha. Now, what do you notice? The sine and the cos are negative. The tan is not only positive, but the tan is 2, exactly what we said without a calculator, right? We found the tangent just using our knowledge. And we also found the sine and the cos. We said the sine was negative 6 over square root 45. Look at that number compared to what GeoGebra says is the sine of alpha, right? And it's not just correct to this, it's correct all the way down, right? We found the exact value of the sine, and we found the exact value of the cos. Cos, we said, was negative 3 over square root 45, which is the same number GeoGebra calculates. Now we have a bit of a problem, though. How do we... okay, so, of course, what we just discovered is that you can find the sine and the cos of any one of these points, basically by observing the x value, the y value, and the hypotenuse. How do you get the angle? Okay, this is a bit challenging. For today, let me just think about this. Let me just think for a second about where we have to go today. Let's do it this way today, and then we'll tackle the bigger issue another time, because this has already been pretty heavy. So for today, what I want to do is this, okay? Let's draw the triangle, just the triangle, okay? Not the fact that it's negative and not the quadrant and all that stuff, just the triangle. I'm going to just take a stab that if I just draw it quickly, I actually get a better result. So yeah, I do. Okay, so I'm going to say this is 6, this is 3, this is root 45. Okay? I want to know what angle is up here. Now, you have 3 choices. You could say sine of beta. I'm going to call this beta. Sine of beta is 6 over root 45. You could say cos of beta is 3 over root 45. Or you could say tan of beta is 2. Now obviously tan of beta is 2 is the easiest one to work with because it's a whole number. So I'm going to do inverse tan of 2. and I'm going to see what does my calculator tell me that the inverse tan of 2 is. Now my calculator, because I'm working with GeoGebra, is ATAN, arctan. Your calculator button is probably a little tan with a -1 in the side. Excuse me, in the superscript. If I do arctan of 2, it tells me that the angle I was looking for was 1.1071. Now you need to make sure your calculator is in Radian mode in order to find this number. So probably there's a button on your calculator called DRG or DEG or mode. You want to switch it from DEG to RAD so that you're getting your answers in radians. If you don't do this, then you need to leave your calculator in degree mode, get the answer in degrees, and then convert it yourself, which you know how to do. You basically divide it by 180 and multiply it by pi. Okay? So when you do this, so if you just did what I just did, and you did arctan of 2, okay, and you're not getting my number, okay, you're getting, let's say if we did it in degrees, if you did, oh yeah, well you know what, yeah, sorry, arctan of 2, right, sorry, I see what I'm, never mind, I gotta switch it to degrees to make my point here. So, ATAN D, never mind, okay, ATAN D I think does it, yeah, there you go, okay, so when you did this on your calculator, you might have got 63.4349. So again, if that's what happened, it means your calculator's in degree mode. You can keep it in degree mode and just get in the habit of taking your answer, dividing it by 180, and multiplying it by pi, right? And that will give you the 1.1071. But it's probably better if you can just get your calculator in RAD mode, and then you can get the answer directly. In any case, what happens when I do this is that I get an answer of 1.1071. Now, it is important to notice that I picked tan as my option here, but I didn't have to, right? So 1.1071, and that's my answer. Now, I could have worked with sine or cos too, right? Let's just quickly show. Arc sine of 6 over square root 45 is the same number. Sorry, I switched it to degrees, so now it's going to give me everything in degrees. Okay, and arc sine, or excuse me, arc cos of 3 over square root 45 is going to give me the same number. So you are free to work with sine or cos or tan. It does not matter, right? They will all give you the answer that beta is 1.1071, and that's what number would go right here, 1.1071. Now here's the thing. We were supposed to find the measure of theta, which is all the way around. That's theta. So think about where my 1.071 is going to come into this. I'm going to draw a full pi to get me over to there, and then I'm going to add the 1.701 to make my angle. So theta is going to be pi plus 1.1071. Okay, and that's my final answer. So let's go back and we'll do theta, alt t, is equal to pi plus 1.1071. And my final answer, therefore, is 4.2487. Now let's go back to where we expected the answer to be. We expected the answer to be somewhere between pi and 4.71. Our answer is 4.2487. And that is right in the zone where we expected it. So I'm raising this point because if you're going to tell me an angle in quadrant 3, you can't give me 1.1071 as your answer. That angle is in quadrant 1, and you need to move it to quadrant 3 by adding pi to it. Okay, we moved it to quadrant 3 by adding pi to it. Okay, and that is going to be our final answer. We can check our work here by doing sine of theta, cos of theta, and tan of theta, and sorry, I'll just switch this to plus g. Okay, and you can see that not only are the numbers right,
but now the signs, plus and minus signs, are also right. Sine is negative, cos is negative, tan is positive. Okay, really important skill. We will come back to this, but I want you to try these ones and see how you do with them. Okay, find the sine, cosine, and tangent of any angle that measures 0, pi over 2, and pi. Okay, so an angle of 0 degrees, okay, if we draw it, is an angle where the initial arm and the terminal arm don't move, and your point is 0, 0. Therefore, excuse me, your point is not 0, 0, sorry, your point is 1, 0, sorry. I was looking at that thinking that's not right. Okay, your point is 1, 0, right? So remember, my circle is like all the way around, and my terminal arm and initial arm and so on are on top of each other because a 0 degree angle hasn't moved, and thus the cos of 0 is 1, the sine of 0 is 0, and the tan of 0 is y over x, which is 0 over 1, which is 0. Okay, we can confirm these things quickly just while you're copying them down there. And we'll go cos of 0 is 1, sine of 0 is 0, tan of 0 is also 0. Okay, and we go to case 2, pi over 2. Where's pi over 2 on the circle again? Well, it's pointing straight up, right? That's pi over 2. The point where it would be located is 0 in the x and 1 in the y. So let's just write it over here. Y equals 1, x equals 0, r equals 1. Okay, the radius is 1 in my circle because I'm going to draw a unit circle. The cos of pi over 2 is equal to the x-coordinate divided by the radius. Well, the radius is 1, so I'm not going to bother dividing by the radius. The sine of the angle is the y-coordinate, 1, divided by the radius, 1. The tan of the angle is the y-coordinate divided by the x-coordinate, which is 1 over 0. Now, as you know, 1 over 0 is an undefined value, and tan pi over 2 is undefined. If you type in tan pi over 2 on your calculator will give you an error. If you type in tan 90, if you happen to be in degree mode, and you type in tan 90, that will not work, right? Because you can't find the tangent of 90 for this reason. The tan of 90 is undefined. Now 180, which is our last one, would be the initial arm over here and the terminal arm straight across, so that theta is pi itself. The coordinate over here is negative 1, 0, and so the cos of pi is negative 1. The sine of pi is 0, 0, and the tan of pi is also 0. Okay, and those are just some key values for us to use for those angles. Last couple of questions here are to look at some reciprocals, try another standard question, and then find the exact value of these trig ratios. Okay, to do this, right, sine 7 pi over 4. So let's get in the habit of drawing 7 pi over 4. Now when you're counting by pi over 4s, here's 0. This is 2 pi over 4. This is 4 pi over 4. Now of course it has to be 4 pi over 4 because it's a complete pi, right? So 4 over 4 is 1. That means halfway was 2 pi over 4. It means our next one is 6 pi over 4, and our final one is 8 pi over 4, which, remember, is just the same thing as 2 pi. I'm just writing it like this just to make drawing what I'm about to do a little bit easier. Sorry. Alright, so I'm supposed to draw 7 pi over 4. Now you can clearly see that 0, 2, 4, 6, 7 pi over 4 would be right here. 7 pi over 4 would be right there. The angle that I care about, the beta, right? The beta angle. is an angle that I make with the x-axis. This is the beta angle. And of course, the beta angle would be 8 pi over 4, the complete revolution, take away 7 pi over 4, which is the angle that I currently have, and I would find that beta is pi over 4. Now, in a pi over 4 triangle, just to remind you from page 1, sine of pi over 4 is 1 over root 2. I know that because that's my special triangle. So look carefully at the workflow here. I draw a circle. I find beta. Let's write this down, actually. Let's write this down. Draw a circle. Find beta. Use the special triangle. And then let's say, step 4, sorry, place in correct cast quadrant. Okay, so let's go through. Step 1, I drew the circle. Step 2, I found beta. Beta is the angle that your angle makes with the x-axis. So remember, the angle that we're drawing here is this one, the big one, the outside one. Okay, 7 pi over 4 goes up to 2, over to 4, down to 6, and then over to 7. Stops here at 7. Beta is the angle with the x-axis. That's here. It's pi over 4. Now I know that sine of beta is pi over 4. Sine of beta, sorry, is 1 over root 2. 1 over root 2. Okay, that's the answer. But the thing is, I'm looking here in quadrant 4. And if I go back to quadrant 4, right, sine is negative in quadrant 4. So what is my final answer here for sine 7 pi over 4? It is equal to 1 over root 2, but it's in a negative quadrant. So my answer is negative 1 over root 2. Now it seems strange, but this is not a question that needs a calculator. This is a question that just needs your knowledge. You need to know your special triangle, you need to know how to draw it, how to find beta, but once you've done those things, you can just collect the answer, okay, that way. Now we can confirm this using a calculator, of course. We can go, what is the sine of 7 pi over 4? And we find out that indeed it is equal to negative 1 over square root 2, right? I didn't need a calculator to get to that, however, right? I have the knowledge to be able to do that. Well, this other one's kind of not the best example, but let's try it anyway. Tan negative 11 pi over 6. Okay, this is B now. Now, here's a good example where if here's 0, this is negative 6 pi over 6, this is negative 3 pi over 6, this is negative 9 pi over 6, and this is negative 12 pi over 6. Okay? Again, I do that because I'm counting this way this time, and you would see that 11 pi, this would be negative 11 pi over 6 would be theta. Now here's an example of what I meant earlier when I said, why would I want to work with a negative angle here? I could work with a negative angle if I wanted to, right? And what would happen here is I would discover that beta is pi over 6, right? Because of course, if you go 11 pi over 6 is this way, it would only take one more to go the full rotation, right? So beta is pi over 6. I am much better off just thinking about this question with a positive beta, with a positive angle. Theta is pi over 6, right? Why do I want to work with a negative angle that goes all the way around, right? When I could just say, I could take my identity, add 2 pi to it, and get the new angle, right? Theta plus 2 pi goes back equal to itself. It's a full rotation. Negative 11 pi over 6 plus 2 pi is equal to pi over 6. And I could work with that number instead. I could work with the positive angle instead of a large negative angle. Now, what is the tan of pi over 6? Well, I have to go back to my special triangles. I don't remember that one off the top of my head. But let's go back to our special triangles. Pi over 6 is here, and the tangent is 1 over root 3, right? And that's my answer, 1 over root 3. It's positive because I'm in quadrant 1, and in quadrant 1, everything is positive, right? So I don't need to make it negative, I just give the answer. Let's confirm. Tan of negative 11 pi over 6 is equal to that, which, by the way, is the same as tan regular pi over 6, and it's the same thing as 1 over square root 3. Okay? So this is where what I'm saying about how to deal with negative numbers comes in hopefully handy. Now, the last one here says secant of 4 pi over 3. This is a very good one to do, so let's do it. Okay, so secant of 4 pi over 3. Now, pi over 3 is a bit of a tricky one to count, because we know that 3 pi over 3 would be there, 0 would be there, 6 pi over 3 would be there. What's halfway between 0 and 3 is 1.5 pi over 3. And what's halfway between 3 and 6 is 4.5 pi over 3. Okay, so I'm supposed to draw 4 pi over 3, which would go right here. 4 pi over 3, right? It would be bigger than 3 pi over 3, but it would be smaller than 4.5. What would its beta be? Right? So here's my big angle. Big angle. Theta equals 4 pi over 3. That's the thing I'm supposed to investigate. Again, I can't investigate it directly, so instead I'm going to look for its beta. Now consider, it takes 3 pi over 3 to get to here, and 4 pi over 3 to get to there. So therefore, the beta in between must be a pi over 3, right? Because to get to 3 pi over 3 plus pi over 3 gets me to where I want to go. So my beta here is pi over 3. Now, in this question, they're asking me about secant. Now, you might not remember with secant, but secant is 1 over cos. It's the reciprocal of cos, okay? Reciprocal. So we need to find the cos, we need to place it in the right quadrant, and then we need to get its reciprocal. So let's go back to the special triangles, okay? So here's pi over 3. It has a cos of 1/2, right? 1 over 2. So I'm going to go down here, and I'm going to go cos pi over 3 is equal to 1/2. But the cos of 4 pi over 3, okay, remember, I'm in quadrant 3. Let's do the cast rule, C-A-S-T. Cos is negative in this quadrant, so my answer is not 1/2. My answer is negative 1/2. Also, I wasn't supposed to give cos. I was supposed to give secant, but that's easy. It'll just cause me to flip my fraction over and give the answer negative 2. So the secant of 4 pi over 3 is equal to negative 2. Let's confirm our thought here. GeoGebra actually has a secant button. Your calculator probably does not. Your calculator, what you can do is do cos 4 pi over 3, and then you could raise that number to the power of negative 1, right? You could find its reciprocal, like we've been doing, and you see that the answer is negative 2. GeoGebra has the advantage of just having a secant function directly, and we can confirm that the value is negative 2. Let's talk through the workflow one more time. I draw a circle. I draw 3 pi over 3, because I want to count by pi over 3, so I do 3 pi over 3 here, 6 pi over 3 over on this side, and then I count the halfway point on the top and the halfway point on the bottom. To draw 4 pi over 3, I draw something in between 3 and 4.5. I sketch it, and then I find its beta. Its beta is the relationship between what I drew and the x-axis. What I drew was 4 pi over 3. The x-axis was 3 pi over 3. So the beta is the difference. It's regular pi over 3. When I check the cos of pi over 3 using my special triangle, I get 1/2. Because I'm in quadrant 3, I'm not going to keep 1/2, I'm going to make it negative, because that's the quadrant where I'm in right now. Then, as a final step, because I'm asked about the secant, I need to just flip it over as an answer, so find its reciprocal. Find the exact values of cosecant, secant, and cotangent of 2 pi over 3. Okay, so let's do that. What time are we at here? Sorry. Yeah, okay, we're getting pretty close to 75 minutes. Sorry, it's a very long one, but it's important. Okay, let's sketch this one. Same drawing we just did. So, same drawing we just did. This is 3 pi over 3. This is 1.5 pi over 3. I'm trying to draw 2 pi over 3, which is somewhere in between the two. This is 2 pi over 3. And I notice that my beta, right? Remember, beta is your relationship to the x-axis. Beta is once again pi over 3. Okay? It would be right here. Because obviously to get from 2 pi over 3 plus pi over 3 would get me all the way to 3 pi over 3. Now, the sine of pi over 3, the cos of pi over 3, and the tan of pi over 3 are as follows. Cos we found was 1/2, sine is root 3 over 2, and tan is root 3. Okay? Just double make sure I got that right. Yeah, okay. Root 3 over 2, 1 over 2, and root 3. Okay? Now, we want to move it, so those are the base values. We're going to move to Q2. In Q2, 2 pi over 3. Okay? Sine is still positive. Cos in this quadrant is negative. And tan in this quadrant is negative. Now, okay, so we did that. Now it doesn't want sine, cos, and tan. It wants cosecant, secant, and cotangent. So cosecant goes with this one. Cosecant of 2 pi over 3 is the same number, just flipped. Secant of 2 pi over 3 is the same number, just flipped. And tangent, cotangent of 2 pi over 3 is the same number, just flipped. Okay, so that's all they're asking you to do there. I know I'm going a bit quick because I just want the video to try to stick to 75 minutes. You can rewind if you need to. Last question is, an angle in standard position, it has a ratio of 3 over 5. What are the other ratios? Cos theta is 3 over 5, okay, which means my angle could be here. I have a radius of 5, r equals 5, right? Because remember, cos theta is x over r. I have a radius of 5, I have an x-coordinate of 3, which means I have a y-coordinate of what, right? Well, let's answer. X squared plus y squared equals r squared. 3 squared plus y squared equals 5 squared. Y squared equals 25, take away 9. Y squared equals 16. Y equals plus or minus 4. Now this is important. It doesn't have to be plus 4. It could be minus 4. I don't know which one of these situations I'm doing. Am I doing the top, which is 3 comma 4, or am I doing the bottom, which is 3 comma negative 4? Notice that in both of these examples, cos is positive, right? This is a positive area for cos. This is a positive area for cos. There is no way to tell which one you're doing. Translation, you need to do both. Y equals plus or minus 4. Of course, this is not very difficult if we understand what I just said, because doing both is very easy. Let's do the first in red. If I'd use the red, cos theta is 3 over 5, sine theta is 4 over 5, and tan theta is 4 over 3. This we're going to call case 1, which is in quadrant 1. The other case we could do is case 2, okay, which is in quadrant 4, which is in Q4. Cos is still 3 over 5, right, because it's positive, but sine in this quadrant is the y-coordinate negative 4 divided by the hypotenuse, 5. Tan in this quadrant is the y-coordinate negative 4 divided by the x-coordinate 3. So I can get the exact values. Again, I don't need a calculator. Just by drawing the diagram correctly, thinking to myself, is there one answer or multiple, and then connecting the ratios accordingly.